Okay, so how many people still have not taken the test yet? Okay. Any questions, studying, reviewing, anything about electricity at all? All right. In that case, let's just have a nice slow day talking about how waves work. Sound good? Excuse me. If you have any questions at the time, though, please do let me know. Let's see. All right. So we've talked a bit about things that all waves share and a couple of the differences between types. But to start with, all waves have a frequency, a wavelength, and those two things multiply together to tell you the velocity of that particular wave. A given type of wave's velocity tends to be capped depending on physical circumstances. That said, mechanical waves' speeds do tend to change if their medium changes, or if the properties of that medium change. The speed of sound in air does fluctuate based on temperature and air pressure. Similarly, let me actually see if I can find a slinky in this back room real quick. It always takes 3 tries to get this door open. Okay, so this is a very long, slinky-like object, and conveniently it's pretty easy to see waves as they travel down it. Would someone mind holding the other end of it?
I'll hold her.
Thank you.
Oh my god.
Very rude chair. Okay. So, just because of its weight versus its length, it's going to kind of hang like this. But you should still be able to see a wave travel down its length. And this is, again, further proof that only the energy is what's traveling, because the rungs that I'm holding onto are not traveling towards her. It's just the energy. Additionally, the amplitude has no effect on its speed. If I pluck it just a little bit, the wave travels as fast as if I pluck it a lot. Only the frequency and wavelength determine, the medium determines the speed, and then the speed relates to one of the other two to determine the other one. But if you change the properties of the medium, I'm going to not really change the effective length, but I am going to make it a little bit tighter by pulling in. By changing the properties of the medium, you do affect wave speed. Like how the temperature and pressure of the air affect the speed of sound. So wave speed only changes with changes in the medium itself. You can pull something tighter or looser to affect those wave speeds, and that actually is one reason why tightening or loosening the strings of a guitar tune it. By adjusting the tightness in the rope, you adjust the wave speed within it, and specifically with a guitar string, the wavelength is what's capped because you're physically holding both sides. So you just changing the speed changes the frequency of the sound. So this is a math-based physics class. It's fine. Slinkies like to go downstairs. That's all it was. All right. So with the information on the board, here's a few, pardon the pun, lightning round questions. What are the frequencies of a 10-meter wavelength sound and a 100-meter wavelength sound? Sorry, 10,000-meter wavelength sound. Oh, wait. I put that in the wrong direction. I'm very sorry. I meant to make that a very small number, not a very big number. 10 meters is already very big. Okay. Changing that from a big wavelength to a small wavelength. Sorry about that. 10 meters is already very long.
Well, the first one for 10 meters, that'd be like 34.3.
Mm-hmm. I made that wavelength too small by accident. You guys agree?
Mm-hmm.
Okay. Now, these provide two different extremes for sound waves in air on planet Earth. This is a very low frequency sound, and typically the smaller the frequency number, the bassier the sound is. At frequencies like this, you tend less to hear it and more to feel the wave physically impacting your body and your eardrum. Because when the frequency is relatively small, the wavelength tends to be very long. 10 meters is a big wavelength. That's a lot of air that has to move for just one whole wave. And when you crank up the bass, this is what is physically impacting your body. Humans can hear sound this low. The lowest that a human can hear is actually 20 hertz. Actually, label now.
So like below 20, is it just feel?
Yes. Right over here, max range of human hearing. You have 20 as the low point, and the high point, the maximum that any human could hear with the best health ears is 20,000 hertz. Below 20, you won't feel it. I'm sorry, below 20, you won't hear it with your ears. If you could detect below 20 hertz sound waves, you would be physically feeling it rattling your body. If you could feel it at all. Sounds that low, if the amplitude, if the volume is very low, you wouldn't really be able to tell. And that can become dangerous because sounds lower than 20, we call them infrasound, can hurt you if you're exposed to them for long periods of time. And you can't tell they're there if they're not loud enough to feel. The vibrations travel through your whole body and start making your insides shake, is how I understand it. So at a certain level, after you're exposed to it for a certain amount of time, your brain and your nerve endings start shaking, which is not good. And because this can happen without a person knowing it's happening, some people have started to use it as a weapon. And I have to see what the Geneva Convention says about that. So, lowest you can absolutely hear is 20 hertz. Lower than that can get dangerous. Highest that any human can hear, and this is the maximum if their ears are in tip-top physical healthy shape, is 20,000 hertz. Meaning you would never hear this. A dog wouldn't either, frankly.
Is that dangerous or no?
I don't think so. Above 20,000 isn't dangerous for humans. We just can't tell it's there. Like at that point, it would be the amplitude that could be dangerous. And I don't know if you'd feel them at all, even if they were high amplitude. We call that ultrasound. And actually, ultrasound tends to be pretty harmless to humans because we intentionally send it into humans in order to check on babies.
What was the other one called?
Infra. I don't know if these prefixes are Latin or Greek or not, but if it's lower than 20, it's infra, and infra as a prefix just means below or smaller than. Greater than 20,000 is ultra, which is a common enough English term. The root word just means bigger than or above. And those terms will actually be used again when we start looking at the frequencies of light. You've probably heard of infrared or ultraviolet. So, fun fact about human hearing before we move on to the others. That 20,000 hertz is potentially the maximum you could have heard the moment you were born. Every second you're alive after that, that top number drops. Because as the cells in your eardrum exist and age and divide and degrade slowly every moment you're alive, that maximum number keeps going down. And it goes down even faster if you continuously don't take care of your ears. I speak from experience, blasting sounds straight through headphones directly into my ear canal. There are sound tests you can do online. It's just a video that continuously plays sounds from 20 hertz up to 20,000 hertz.
Then how do you know
Hmm?
that someone, like, what measures this?
Scientists have just done a lot of comparisons determining what sounds a child can hear versus an adult. Um, I might not be able to play it super well for you guys, but I can at least show a sound test. These things are all over YouTube, and there's similar videos that will just... Okay, sound test hearing range. That's the one I've been using. This video constantly just runs through all the sounds that a human could hear. It might not be making any noise at the moment because when it's on the projector, it's trying to connect to the projector's audio system, which doesn't exist. But it just runs through all of them, and I've taken these several times, and about at this point, you can start to vaguely hear those low bass tones. They tend to feel very low volume, so you got to crank the sound up at this point to be able to hear it. But most everyone can hear this once I turn up the volume. As the video goes on, though, and the frequencies get higher and higher, they feel louder and louder. So if you do this at home, crank the volume down slowly the length of the whole video. And this track is 6 minutes long. It's pretty safe to skip through all the low frequencies. And eventually it just goes up super high and keeps getting faster and faster. And what I usually do when I have a working sound system is ask everyone to raise your hand when you can't hear it anymore. Mine caps out at about 15,000. And I guarantee, at the very least, because you guys are younger than me, yours should cap out later than that.
Why does it look like that? Why does it look like it grows?
That is an illusion when the frequency changes. Kind of like when a tire is spinning and at some point it kind of looks like it turns around or doubles back. That's just an illusion. The eye can't track the speed of what's happening. If I put this on my computer, I might be able to play it out of the computer's speakers. So I have to disconnect it. Okay. That's 25,000. That's 2,500 hertz. 2,500. I'm gonna jump up towards the end now. 6,000 hertz. 10,000 hertz. Okay, so raise your hands when you can't hear it anymore.
Okay.
Holy cow. Best ears in the room. And you're furthest away. Okay.
So there's something playing right now?
Not right now. But back up just a hair. And I'll put it towards you guys.
Yeah. It's not as bad as I thought it was. I thought it was more death.
Most elderly humans, like 60 plus, can hear to about 10,000, and that's where it tends to stay for the rest of their lives.
10.
What that means is most sounds on Earth that humans need exist between 20 and 10,000, But as you age, you do lose some of those upper frequencies, so things just start sounding different. And it's probably one reason why the young and the elderly can't ever agree on music. Similarly, both adults and children have figured out how to weaponize this particular fact. Adults have started putting speakers in front of grocery stores that's constantly playing high frequency sounds that the paying adult customers can't hear, but that the children loitering outside can. They built a grocery store across from my high school, and for some reason all the teenagers decided to just hang out at Food Lion. So they installed those. Less students hanging out at Food Lion. Kind of mean. No, very mean, frankly. But on the other side of things, some students have realized that if they make their ringtone really high frequency that they can hear, there's a chance their teacher can't. That said, I wouldn't much care for my I'd care for my ringtone even less if it was just a high-pitched whine.
So like do deaf people, like obviously they're like frequency is lower because they can't hear. But, like why?
Sorry?
Like deaf people?
Oh, there's any number of reasons why someone's ears might not work fully or correctly. The eardrum itself might be damaged. That's like if the very output of the speaker doesn't work. Eardrum itself, any of the bones inside of your ears that transfer sound from the drum to your nervous system, any part of the nerves between your ear and your brain, or the part of your brain that interprets sound. If any of those are damaged, suddenly your ability to perceive sound at all is impaired.
So that means that there's different like types of hearing aids depending on what.
Yeah, there's some people who just need the sound to be louder, and so their hearing aid just plays it louder. There are some people who need a cochlear implant that literally goes into their head to skip past whatever part is damaged. So, those are some of the minutiae of sound. Next, using the same formula, what frequency of light would this wavelength of light be? And I will show you in a second what frequencies of light correspond to what colors.
I don't understand how volume ties into this.
Velocity. That's small v for velocity.
So the higher the volume, the higher the velocity?
Oh, you mean the volume of sound?
Yeah.
It doesn't. How loud something is does not affect its speed.
Then why do we have to turn up something that's a low frequency to hear it?
Well, just because we can hear 20 hertz doesn't mean it's easy. It's like we have the equipment to, but it's not within our optimal range. It's like my normal hammer could bust open rocks, but it's not made for it. Or my rubber mallet could break rocks, but it's not made for it. Well, that might be one reason why the elderly have so much trouble hearing. It could be when you approach your limit, the sound just gets quieter. And we all have the same lower limit. Fun fact, though, actually, while you guys are looking at this math, the range of hearing for a dog, because they famously can hear sounds we can't, is about 40 hertz to 40,000 hertz. So there's at least 20,000 more hertz of sound the dogs can hear that we can't. Alternatively, there's low sounds we can hear that they can't. Not much of a superpower on our part, but it's neat, I guess. But any dog whistle that you've ever played is somewhere between these two frequencies. I think they're about 30,000 hertz. I was about to say any dog whistle you've ever heard. If you've heard it, it's not a dog whistle. But volume has no effect on speed, frequency, or wavelength. It's simply a measure of the energy, the amplitude of the sound wave.
Wait, which volume are we talking about? Like,
Sorry, sound volume.
okay. Negative 9, yeah.
Yes, nano is times 10 to the negative 9th.
That's a really big number.
It is a very big number. Do we agree? Okay. 45 does repeat for me. I'll just put that there. And in terms of metric prefixes, kilo, mega is 6, giga is 9, tera is 12. So this would be 545.45 repeating terahertz.
Wait, I thought we just said Tara was 12.
Yes.
Oh, you moved it to the right. Right?
Yes.
Yeah.
.45 times 10 to the 2 terahertz would be the same as this. And, oh, I did this right. Boop. This is the band of frequencies and wavelengths for light of every color that the human eye at optimal functioning can see. And so we did 550 nanometers. That would be, and yes, 554 point something terahertz. So that would be green.
Is it the same thing for like blind people? Like there's different reasons why you can't perceive certain colors?
Yes, sir. There's reasons why you wouldn't be able to perceive certain colors. There's also loads of reasons why your sight might be damaged to any degree, because with the ear, sound has to hit your eardrum, the signal has to go through all the bones, get into the nerve ending, travel to the brain then has to interpret it. It's very similar with the eye. Light first has to get into your eyeball, hit the back, trigger the rods and cones. That signal has to go through the optic nerve into your brain and then get interpreted. If any of those steps can't happen right, you can't see right.
But like, can't you not fix color stuff for eyes?
That depends on why you can't see the color.
They made like glasses and contacts for blind people if they want to see color. Like you can wear those, and that'll make you like. For some people, it works.
Yes, for some people's color blindness is due to, I'm skipping ahead a little bit in my notes, but it's all relevant. we only have one eardrum to interpret all sound. All sound hits the one eardrum, it all works normally.
Like one per ear.
One per ear,
Yeah.
right. But still, within each ear, there's just the one thing that receives all sound. Light works a little bit differently when it enters your eye. So this is going to be a very quick jerry-rigged eyeball. So light enters the eye. The eye's lens is going to cause the light to flip and project itself onto the photoreceptive cells on the back of your eyeball. Those cells are called rods and cones, and they are designed to receive light, kind of like the chloroform of a plant. The cones detect color, the rods detect light versus dark. So rods tell you whether or not it's bright or it isn't. Cones tell you what color you're looking at. So already that's splitting the task between two different types of cells. If your rods are damaged, you might not be able to tell the difference between night and day. If your cones are damaged, you could see correctly, but in grayscale. If you had no cones, if you had no cones at all.
But night and day are like two different colors. Like why wouldn't you tell a difference?
Well,
you know what I
okay.
mean? Like
Talking about rod damage doesn't come up very often. You might not be able to tell between different like lightness and darkness of the same color. Pink and dark red might be imperceivable. What is talked about more frequently is cone damage, because your cones, they don't automatically just see light, say, oh, that's, mint green, and send the signal mint green to your brain. Each cone is a bundle of different detectors that each detect a different color. Most human eyes have cones for red, green, and blue. Because in terms of physics, these are the primary colors. Art has a different color wheel. When light enters your eye and it triggers the cones, it'll trigger different combinations of these cones based on what color it is. Red light triggers the red cone, yellow light triggers red and green at the same time, purple light triggers blue and red at the same time. And depending on what gets triggered, it sends a signal to your brain, and it then interprets that color from that signal. If at any point between the light hitting the cells and the signal getting to your brain, something gets garbled, your ability to see that color malfunctions. And there's one type of color blindness that is due to a specific error when specific colors trigger the cells and the signal gets confused by those colors. So because those confusing colors enter your eyeball, it interferes with the eye's ability to see other colors, or sometimes any color. Certain colors just can't be processed, and they interfere with the processing of other colors. So the types of glasses that you're talking about filter out those colors that trigger the issue. And with those not there, the rest of the eye can function normally.
so you don't see those colors?
Right. It filters out the specific wavelengths that come in and bang drums on everything to mess it up. The other ones make it fine. I think I've seen like the videos where they first got the glasses and first put them on. I think the colors that I most commonly heard them say, I've never seen that before, were maybe pink and purple. Yeah, I think it was a shade of red that was causing the problem, actually. So yeah, if any part of the chain between here and your brain interpreting the signal glitches at all, your sight is compromised in some way. This thing is the most complicated part of your body. That's why if it's damaged, there's probably no going back. Your brain, different parts of your brain can learn to pick up slack for other parts. Your eye can't do that.
Can't you have like an eyeball transplant?
I don't know if we've done that successfully, because you'd have to remove
Connect
the
it to
eye,
your brain.
sever the nerves in an intelligible way, and then take a different eye and reattach the nerves the same way, and then jam it back in their skull.
It's not actually floating, but like kind of in a way like it is just kind of floating. That you want like one thing attached to it. That's why like if you like, that's why like even scratching your cornea can be really bad.
Well, I'm sure you could like take your eyeball out if you wanted to. I mean,
Yeah, people have like glass eyes. Like when you lose an eyeball.
Yeah.
As of 2016, the end of 2016, this article reports that parts of ocular systems had been transplanted, but at the end of 2016, they were aiming to attempt the first whole eyeball transplant.
I mean, that'd be pretty cool.
It would. It looks like the parts that are most commonly transplanted are just the parts on the front, because that's easy to get to without tearing someone's whole head open.
You like the color part?
No, I mean like the lens. Ocular surgery by taking someone else's cornea and putting it on your eye.
I don't get how cataract surgery isn't more dangerous because like with cataracts you can replace like the film that fits in your eye. Like I think that's still dangerous.
Can be.
What do you mean, dangerous in the surgery?
Well, like it's just like the eye is so delicate. Like how would you not like terrified? Like, it's, like you have to like.
Oh yeah, I'd be terrified.
Because like if you make one wrong, really make like it's just like it's like a jelly thing. Like, it's not like a bone or like skin that you can just put back on.
Do they perform that procedure while someone's awake? Because I'd be terrified of just, looking away.
I don't think so, but like, you have to keep your eye open. So I don't know. I just remember when I was in 10th grade, we like read about like North Korea and like how like strict it is, and like they had a doctor over there, like a lot of people got in trouble because like they were he was fixing their cataracts, and it's just like they had to like watch the surgery. It's such an odd surgery.
I don't like it.
Well, isn't like LASIK just tearing off one of your little layers?
I think so.
I think that's what's happening, just tearing off many layers.
I've not looked into the specifics of that procedure. All I know for absolute certain is, you know what? I don't even know what I just told you for absolute certain, because now we're mixing in biology, which is not my forte in the slightest.
Some color blindness is genetic, obviously. That's like everyone should know that. But and I think red green is the most common color blindness out of them.
I think that's what I've heard. And this seems like as good a point as I need to bring it up. There's a reason that I didn't put any rods or cones in the back middle here. Because, and again, biology, so grain of salt. You guys could probably, all the bio majors present might be able to speak better to this. That's the part where the optic nerve connects to the physical eyeball. There's no rods or cones there. There can't be, because there's optic nerve there. Which means that if light hits this, there's nothing to sense it. There's a blind spot in each eyeball where light will come into your eye, but if it hits right there, it's just, the signal's gone. You receive no information. Every single eye has a blind spot hovering in the corner. And to draw two eyeballs as seen from above, the nerve kind of connects towards the back inner corner, so the blind spots are out in this direction.
But can't you just move your eyeball?
Now that said, you've probably never seen a hovering black void in the corner of your vision. At least I hope you don't. Because the brain knows that blind spot is there and fills it in with surrounding color. Because if you had a hovering black dot in the corner of your vision, at least if it was me, I'd go insane. More insane. And what can happen is, if something is completely engulfed within that blind spot, if there's like a shape or a dot completely within the blind spot, it just gets filled in and you can't see it at all. So, and you can do this at home, you can do this here at home if you want. If you take a blank sheet of paper and put 2 dots on it, if you want to test your left eye, close your right eye, center the right dot over your left eye, and draw the paper to and from your face. Eventually, the rightmost dot will just vanish, but only if you're looking straight on at the rightmost dot. Yep, there it is, gone. All you need is a page with 2 dots. Okay, last one of these. You hear a thunderclap 5 seconds after the lightning bolt. How far away is the lightning strike? This is less about this formula and more about the normal velocity formula. E equals d over t. For the sake of simplicity, let's assume that the light is fast enough to be instantaneous. Let's just say the light from the lightning travels from the bolt to your eye at time of 0, and then 5 seconds later you hear the thunderclap. How far did the sound travel in 5 seconds?
Isn't it just like 15 to the 8th?
Sorry?
Isn't it 15 to the 8th? V equals D over T. Yeah.
I'm not sure what you're saying or where that number's coming from.
Okay, V equals D over T, right?
Yes.
V is the 3 times 10 to the 8.
That's, the light from the bolt is going to travel so fast that it's going to reach your eye in like nanoseconds. Notice the extreme difference in speeds between these 2 numbers. Light is like at least a million times faster than sound.
Oh, wait, are you tracking the sound?
Yes. You hear a thunderclap 5 seconds after the lightning bolt. And the reason that this happens is because light and sound travel at different speeds. I've seen on shows like Mythbusters where they set off a big explosion in the distance, and the camera on the show, you can always see the boom before it actually records the sound of the boom. And it's just due to the sheer difference in the speeds. The light will always reach you faster than the sound. So, in meters, how far did the sound have to travel in 5 seconds?
Like 1,715.
Correct. You guys agree? All right. And that is a pretty valuable tool for figuring out how far away the lightning strike was. Similarly, you can do, just as a reminder, D equals D over T. You can do something similar with an echo. If you scream into a cave and track, takes 3 seconds for the sound to get back to me, you can use that to figure out how deep the cave is. But if you plug in speed of sound and 3 seconds, that distance you get will be twice the depth of the cave.
Because it went there and back?
It went there and back. So echoes, same trick, but the distance will be double, and you have to take that into account. And bats and dolphins just do all that math in their head.
Do whales have echolocation or just dolphins?
They do. I think most aquatic mammals do, actually. I know some seals do.
Wait, what? It's a dumb question. Why do they need it again? So, what?
Sound travels, well, light still travels faster than sound. But underwater, light gets murky the further out you go. There's a maximum range to how far you can see underwater, even if you're an aquatic creature. But sound travels very far and very clearly underwater. So since your sight is just less reliable down there, a lot more creatures rely on echolocation, including, apparently, as far as I'm aware, most aquatic mammals. I don't think fish do. I think it's just a mammal thing.
I don't even know what fish see. Like, what do they see? Like, I
Well,
don't.
apparently mantis shrimp see a lot.
Most whales and dolphins use, like certain whales use echolocation because their sight isn't as good.
Probably. I mean, again, you can't see super great down there, so why rely on it?
But
At least
you
that's
don't
what I
need to
saw
see.
in Dory. In Finding Dory, there's a whale. And they talk about it, and Disney is there too, that she can't hear those red echolocation, like the ones with the big forehead.
Oh, the beluga.
Yeah. Because they can't see them. They use echolocation more than they see. Or it's something like that.
The sight quality of whales. Oh, yes, at least at a preliminary Google search, white whales have pretty poor eyesight compared to humans. You can see about 10 times worse than humans. I think their eyes are just for fighting the things that are so close that sonar becomes pointless. Sonar for long range, sight for it's in my face and I want to eat it. All right. Sorry, you guys can go. Didn't mean to hold you up.